All right, I'll start one more time. Start from the very beginning. This is 8.3. It's something called composite functions. It's just a special name for something you have already done. What is composite functions? In a nutshell, it's when you have a function that is inputted inside another function. So for example, g of x is inside f of x. So these are the two components. This section is something you have already done in the past. I've sort of snuck it in before without actually teaching it because conceptually, it makes a lot of sense. The only difference is I'm going to show you some new notations, like it's not a multiplication, it's a hollow dot. I believe the name for it in other subject could be a knot. I think it's K-N-O-T, right? Like F naught G, or just F naught G this way. It's read when you see it this way as F of G of X. Okay. So let's talk about that. You'll see me use this language and these kinds of ways of describing it as we move on. All right. Let's take a look at some simple examples. A composite function, as I said, is not a new concept, but the new notations make communicating it easier and more efficient. Like we as mathematicians do not want to take g of x, x squared plus 8, and write it inside here every single time. Instead, we communicate it with function notation, fx, gx, so on and so forth. So here we go. Given the functions f of x is equal to x minus 5 and g is equal to x squared plus 8, determine h of x, which is f naught g, or f of g of x. Well, what does that mean? Well, f of x is supposed to be that. Oh, let me write this. This is f of g of x. Okay, so f of x is supposed to be x minus 5. I'm going to say x minus 5, right? That's right here. However, what is the x value for f? It is this value. This is supposed to be the x for the function. But instead of giving an actual x value, it gave me another function to input. So every time you see the g of x, you are going to plug in g of x, x squared plus 8. So h of x actually equals to this value. That's it. And I think I made a typo here. G of x should be, let's scratch this out and do a new one. This is G not F. What does that look like then? Okay. At this point, I realize that some of you may not have gone through the daily routine of printing out this sheet. Either take out a piece of paper if you don't have a printer, or print this out and follow along with us. I'll go slowly so that you have an opportunity to do so. This is also being recorded, so, you know. J of x, same thing. J of x, or G not F, or G of f of x, is the same as saying, I have G of x, but instead of an x value, I'm plugging in a full function, an entire function in there. So let's rewrite it. G of x is x squared plus 8. So what is the x value? In this case, it should be in here. But instead of a number, they're asking me to plug in an entire function, which means x is going to be rewritten as f of x, which is x minus 5 squared plus 8. And so I could open this up and I could rewrite it, but this essentially is a vertex form. So it's not a bad form. It's a nice one for a quadratic. So I'm just going to leave it. Who joined us so I can update the, oh, Mika. Welcome, Mika. Did you sleep in? Yes. Yes, I did, Mr. Kim. All right. Sounds good. All right, done. That's it. That's essentially it. Mika, I'll take this slow. So why don't you go to Brightspace and print out a sheet for 8.3 for us, for yourself? For everyone else, are there any questions? Going once, going twice. All right, then let's move on. So if that is the case, I am going to see how h of 2 and j of -3 play out. Please note that the superposition principle still applies, right? Remember, h of x means all the component functions inside is also going to have x equals 2. What do I mean by that? Well, h of x being g of f of, f of g of 2. Oh, sorry. Because h of x is the same as f of g of x, h of 2 means whatever value of x I need in the components will follow suit. It'll be like that. Okay, so let's do it. What is g of 2? G of 2 is 2 squared plus 8, which is 4 plus 8. That's a 12. Therefore, you plug that into f. Sorry, maybe I should highlight it just to make sure. So g of 2 is equal to 12. And so this portion is going to be plugged in as a 12. That's where I'm getting this number. F of 12 is equal to, let's see, f is the same as x minus 5, so it becomes 12 minus 5. The final answer is 7. Therefore, h of 2 is equal to 7. I'll do it one more time. This time we have j of -3. And please remember, from our simplified equation above, j is this formula, or this equation, excuse me. And also, by superposition, right, which is equal to g of f of x, if the x value inside the function j is -3, that means all the x values inside the components are going to be -3 as well. And so what does that equal to? It equals to a -3 minus a 5. Oh, sorry. I realized I did it separately, didn't I? That means, let's see. So let's start with f of -3. That is equal to -3 minus 5, which is -8. And that value, f of -3, which is -8, is going to be plugged into the g function. So g of -8 is equal to, where's my g? X squared plus 8. So -8 times -8 is 64, plus 8 is going to be 72. Now at this point, you might be thinking, do I have to solve all the components separately? No, I did that as an extra piece to show you that by superposition, instead of plugging into each component separately and solving it, if you have the equation already, you can plug it in too. Let me demonstrate up here. Because I sort of don't have space. If you have space underneath, you can do so. Okay, h of 2 is the same as 2 times 2, 2 squared, right? Plus 3, which is 7. They agree. In the same way, get this out of the way. There you go. In the same way, j of -3 is the same as -3 minus 5 squared plus 8, which is -8 squared plus 8. which is 64 plus 8, which is 72. And these two agree. All right. Any questions? Going once, going twice. All right. If there are no questions, I'm going to start introducing some interesting things that we can do for composite functions when something is inside another. What that means, what kind of like, sort of T questions or trick questions we can ask. Things that we can ask about domain and range. What else? How that might connect with polynomial functions or power functions we've done in chapter 1. So let's take a look. Use function composition to verify that the following functions are inverses of one another. If you remember, if you do the inverse, so if you plug in an x to get the y, but you use the y to get to go back to the function, and you could get the x. Scratch that. So you know that if you do an inverse of a function and then you scratch that. How do I explain this? Why am I so lost for words? So function f and f of -1, essentially you can think about it as I am using the x to calculate the y. I am using the y to calculate the x, right? So they are essentially flipping each other back and forth. So I should, whatever value I plugged in, I should get that value back out, right? So essentially, if f of x and g of x are inverses of each other, I should be left with just the value of x. If I do not, then they are not inverses of one another. So let's try it. So assuming if g of x happens to be the inverse, if g of x is in fact the inverse of f of x, then I can plug in I can plug in g of x into f, and I should just get that. So that's what this question is asking. Prove that if you use these two functions as a composition, then you will only get x left. Here we go. All right, let's do this. If I do this, then I would get x minus 1 divided by 2 times x, right? X minus 1 divided by 2 times x. But instead of the x, I need to plug in g of x every single time. What is that? It is negative 1 over 2x minus 1. And here it's negative 1 over 2x minus 1. Yeah, it's a little messy, but only because it's fractions. So let's take our time with it. I might need space, so here we go. I'm going to solve the numerator first. And in the numerator, I need the same 2x minus 1 over here. So it will be negative 1 over 2x minus 1 minus, well, it's a 1. So I can rewrite a 1 as 2x minus 1 like that, because this is equal to a 1. Next, 2 is being multiplied with the entire fraction. So 2 over 1 times a negative 1 over 2x minus 1 would be a 2. Okay, let's simplify it. Here we go. Keep up with me. Same denominator. This is a numerator, okay, people? This is a numerator. -1 minus 2x plus 1. -1 minus 2x plus 1. So the -1 and the +1, they will cancel each other out, turning into a 0. The numerator is just -2x over 2x minus 1. I don't think I need this large of a thing. Okay. Next, on the bottom, it's still just -2, 2x minus 1. Following, I have a fraction now. I can't simplify the numerator. I can't simplify the denominator. So I have a fraction divided by a fraction. And you know where this goes. You know what it is. We got fraction dividing by a fraction, which I am going to rewrite as a multiplication of its reciprocal. So these two reduce into a 1. We have -2 and -2 dividing into a 1. All that's left is an x. Therefore, f of x is an inverse of g of x and vice versa, of course. As an extend, please note that you could have always tried to prove that f of x is a inverse of g of x by turning this into y, equals 1, -1, 2x minus 1, and then swapping the location of x and y. But the question did ask you to use function composition, and so I didn't do that. Someone like Adnan would be like, yo, isn't there an easier way? I thought about it this way. Why can't we do it this way, Mr. Kim? This is why, Adnan, okay? I think I know you guys too well now. Any questions about this? No? Really? I hope it's really that this seems okay, just following. Example 3. Sure, important. A different style of question. Example 4. Similar style question, but I think it's worthwhile doing. And example 5, you know what? They're all worth doing. So you know what? Today, I might end up doing this entire sheet, which means we might have to extend a little further before I set you off on a break, okay? Here we go. F of x is equal to x squared. Find g of x such that the composition is going to be a trinomial of that sort. Can you let us try some on our own too? Oh, that's a good point. I'll set you up for this one. Here we go. F of x. F of x is defined as this, right? And you're supposed to plug in an x in there. But if I had g of x, I have this, right? And if that is also true, it should equal x squared plus 6x plus 9. So essentially the question is, what squared gives you x squared plus 6x plus 9? That's the question. This, honestly, if you see it, you see it. If you don't, you don't. I'm going to give you a minute to see if you can identify the solution and solve it. The answer? I'm hoping you noticed that x squared plus 6x plus 9 is a perfect square trinomial. If you factor this, it's x plus 3 times x plus 3. In other words, this is x plus 3 squared that gives you this final answer. Therefore, g of x is x plus 3. That's pretty much it. Here's a slightly harder one. Same thing here. If g of x this time is x minus 3, find f of x such that f not g, or f of g of x, is equal to this. And this might require a bit of reverse engineering, but that's okay. What do you think? And know that this might be an open-ended question because there could be more than one answer. So I'm going to put that as an example of a T question. I will give you, how about I give you 3 minutes this time to see if you can figure out a good approach. Okay, so I actually forget my own solutions to this. And so we're going to go in blind, like we sort of typically do anyways. I sort of find it, I actually, semi-intentionally, I actually don't try to keep too many answer keys to questions like this so that I can showcase my own, I guess, thought process. Let's try it, okay? Whatever the case may be, this has to be where I start. So I'm going to just, it's going to be a reverse engineering process. Okay, from here, I notice that I have an x squared. How do I get an x squared? Well, the only way to get an x squared is to multiply with another x. So I'm assuming that it's going to be multiplying with another value of itself. It's going to have to be one of these. Some of you might be saying, oh, why can't I just add x? No, that's not the case because f of x, every single time an x is there, it has to be in the form of x minus 3, not just single x. There's no way this can exist. All right, think about that. So I'm going to say, okay, if x minus 3 has to become x squared, then I need to square that. But if I do this, that actually equals x squared minus 6x plus 9, right? How do we keep the x squared, but how do we get rid of a negative 6? Wouldn't we have to add a 6x? But once again, you can't just have x there because anytime I'm plugging in an x, it actually comes in the form of x minus 3. So this would actually be 6 times x minus 3. That's why I have a positive 6x and a negative 6x. So it has to be this. Again. And next, if I did that, well, from here, I have a positive 9. From here, I have a negative 18. They have to add together to give me a negative 11. So right now, this adds to a negative 9. So I need an extra minus 2 there. So it has to be that. So from if x minus 3, whatever needs to happen to become x squared minus 6, well, that means f of x must have been that value squared plus 6 times that value minus a 2. So that when I plug in x minus 3 there, and when I plug in x minus 3 there, they will add up and cancel each other, whatever, leaving you only x squared minus 11 left. Maybe I haven't explained it in the most, I guess, concise and clear way possible. Any questions on this? If you'd like me to repeat, I can do so as well. No? Everyone's okay? All right, that's good. All right, here it is. So example 5 is a bit of a thinking question. This is what I want to leave you with. I think it's worthwhile. Number 6, yeah, we'll do number 6 together because it talks about domain and range again. But I want you to really try this. This time I'm going to give you 5 minutes and I will pause the video. Yeah, if I have f of x, and then I have x of t, okay, I did that on purpose, okay, f of x, and inside x is a t, you get it? And then t is t squared plus 2. And inside the t, there's a k. Find a simplified expression for y equals f of k. So you might see a lot of examples like this in university, right? Where whatever variable that we are using is with respect to a different variable. And if you want to find what that variable is, that's actually with respect to another variable. And they assume that you will understand just by, without me even saying it, without the professor or the textbook even saying it, that you can intuitively just match and assume that this is a composite function. It's sort of like a very common language once you sort of do more and more of these. It's sort of like, yeah, that's what it means, right? So give it a shot. I will pause here and give you 5 minutes.
To do this.
It's time to do this. Okay, let's just get to it. F of, let's see. So f of x, yeah, f of x is going to be 3x minus 2, right? Which is the same as 3 of t squared plus 2 minus 2. And see if I could color code this the same way I did before. So x is going to be red. Blue. Oops. And then from there, yes, it's t squared, but t itself is 3k minus 2 squared plus a 2, which would be in green. And so if I were to simplify, I finally have f connected with k. So 3, let's open this up. This becomes 9k squared minus 12k plus 4 plus a 2 minus a 2, which is 27k squared minus 36k, 12 and 6. That's 18 minus 2. So my final function is 27k squared minus 36k plus 16. Might want to correct me if I'm wrong, but I think I'm. Any questions? And that's it. I think we can actually finish this before the break then. All right, let's clear all. Actually, if you were looking for it, if you still wanted to see some, go for it. The final bit, given the functions cosine as well as a parabola, determine the domain of, when I multiply, determine the domain of division, and determine the domain of a composite function. Again, I wish there was a simpler way to talk about maximum domain and range of multiplication or division. There are some things you can do to help you understand it. For example, knowing that it's a product, I'm not creating any special restrictions. And so I know that for domain, the domain will be a common thing between both. For the domain, recognize that cosine, it could be any number. Because I know this is a parabola, without doing any math, I know that this is going to be any number. Like, I think you understand, like this goes on forever. Okay. And for a parabola, well, it goes on forever in the left and right direction. So even if I multiply, it wouldn't change anything. Domain is there. For the range, however, it didn't say anything about the range. Well, there you go. I don't even have to work on it. It's not even that hard. For the next one, please note, for the domain of y equals, again, it's nothing different, right? The top part, you can say that it's going to be XER. I don't have to worry about it. In the denominator, it's also XER, but we can't have this portion equal to a 0. So that's the only situation where we would have a restricted domain. So go back to this function and figure out when this equals to a 0, which is xx minus 3, minus 6 plus 1. And so x would be a 6 or a -1 if the denominator was a 0. Therefore, for part B, x belongs to real numbers such that -1, no, x cannot be -1 or 6. There you go. Okay, I did the first two relatively quickly because a third one is a little bit more time consuming. All right. Let's see. All right. If you have a parabola inside a sinusoidal function, let's see what this turns into. This is cosine of a parabola. And Oh, yeah. So this one's a little bit funky. Actually, no, it's not. Is there a restriction inside the parabola? The answer is no. Okay, why? And then the y values of this quadratic equation are what's going to be plugged in to cosine. In other words, are there any values of y that cosine will not be able to handle? Just think about it very casually. The y values, it only goes to a certain negative. And can cosine handle negative as an angle? Of course it can. And this will continue on to be positive infinity. Can cosine handle any values of any degrees all the way up to infinity? Of course it can. Therefore, for this function, the x values can absolutely be anything we want. So there's no restriction. The only time there might be a restriction is if the y value of this function somehow turns this into an error, which in this case it won't. But there are cases where it might. For example, what if I gave you a what if I gave you a tangent of x squared minus 5x minus 6? Right? You know that for the tangent function, ever so often there are vertical asymptotes, right? Which means, here, let me move this up a little bit so that we have some more space. Let me erase this. And let me erase this. Okay. Which means I need to find all the values that give the vertical asymptotes, which means I need to find all the values of x that make cosine in the denominator a 0. Right? Which is annoying. Yes, I know. I'm not going to ask you to calculate either. That's why I didn't give you something like tangent. Because we need to figure out, for cosine to equal a 0, we need to figure out when x squared minus 5x minus 6 equals a 0, when this equation also equals, no, not 0, sorry. When this equation equals a pi over 2, I also have to figure out when this equation equals 3 pi over 2, right? That will make cosine a 0, which will make the entire fraction undefined, right? That's annoying. I get it. So I'm not going to ask you to do it. But composite functions, when I ask for the domain, you might want to take it slow and see if there is anything that requires extra thinking. Okay. I'll pause here or stop here. Any questions?